All right, so today we're going to talk about, oh, slightly better attendance today. That's good. So today is our 13th lecture, and we're going to talk about an interesting phenomenon which is called Landau quantization. So we've been looking at free electrons, mostly inside metals. In the first lecture of this module, which was lecture number 11, we saw how the energies of these electrons were quantized, and the k vectors belonged to the reciprocal space. And the k points were all quantized. In the second lecture, we looked at some thermal properties of these free electrons. Now, in today's lecture, we are going to explore even further the concept of how these free electrons, whose energies are now quantized, they lie on a grid inside the reciprocal space. How do they respond to magnetic fields? We've seen this in passing in the previous lecture when we were discussing the spin split bands. So if I have energy here and the density of states on the vertical axis, I can draw an energy density proportional to the square root of energy for the spin up electrons, and likewise an energy density for the spin down electrons. And both of these spin split bands are filled up to the Fermi energy at 0 kelvins. Now, if I have a spin inside a magnetic field, its energy goes up or down. So if you talk about a single electron, the energy in the presence of a magnetic field can go up and down by mu BB, depending upon the direction of the spin with respect to the magnetic field. So if this system of free electrons, which are called poly electrons or a poly gas of electrons, is subject to a magnetic field, we've found out already that one of the bands lowers its energy and the other band increases its energy by this much. So in the vicinity of the Fermi energy, around here, there is a mismatch of occupancy. So the spin down electrons, they have high energies, but they already see vacant energy levels here at the same or even the lower energy. So what they would like to do in the process of equilibration is to flip their spins and acquire the lower energy. That's what every system would like to do as it achieves equilibrium. So once equilibrium is achieved, the new density of states looks like the following. This is what we have. So we have more spin up electrons than spin down electrons. And this polarization difference between spin up and spin down electrons, if you multiply this with the spin on each electron, which is mu b, you will find out a total magnetization of the system. So all the action in condensed matter physics, especially for metals and semiconductors, takes place in the vicinity of the chemical potential or the Fermi energy. So we really need to calculate, and if you do the calculation, we already did the calculation in the previous lecture, the magnetization is going to be proportional to the density of states at the Fermi energy. So the density of states at the Fermi energy is important. The real action and the drama takes place in or near about the Fermi energy. So this is a really important concept. All the electrons that are well below the Fermi energy, they don't participate in conduction or heat transport or magnetotransport or conductivity because they're all stacked up, they're all stuffed, and they are all in a claustrophobic situation. They have nowhere to go. There are no empty levels nearby. It's only that in the vicinity of the chemical potential or the Fermi energy at 0 kelvins that new spaces can open up. The parking lot for electrons can open up, and electrons and cars can go into those empty parking vacant spaces. So that's a really important concept in condensed matter physics. Now, this picture that we've described so far talks about the spin of the electron, but it does not take into account the motion of the electron, the spatial motion of the electron, or the orbital motion of the electron, because these electrons are conduction electrons. They are in the conduction band. They are coming from the valence electrons that have been stripped off from the atoms, leaving bare the ionic cores. So these electrons can also move around, and when we impose a magnetic field on these electrons, their spatial motion is also going to be disturbed. So now what we're going to do today is look at this concept of Landau quantization and see how the magnetic field affects the spatial or the orbital motion of these electrons. Now we can use the term spatial motion of electrons synonymously with the orbital motion of electrons. But remember that these electrons are not really inside an orbital. They are free electrons. So any questions before we proceed forward? So the basic idea that we must all remember is that if I have a magnetic field, B, I denote the magnetic field by B, and suppose I have an electron, and the electron is free to go anywhere. So if this electron has a certain velocity, say a velocity vector V, a force is going to act on this electron, and that's the Lorentz force. And that force is going to be given by QV cross B. So this is a classical picture that I'm presenting for the time being. This is going to be equal to minus EV cross B. So if I were to take the cross product of V cross B, a force is going to act on the electron. As this force acts, the electron goes round in a circular orbit. Okay, so it takes these loop-like motions. And this force, this electromagnetic force, actually provides a centripetal force, which is given by mv square over r, where r is the radius of this loop. So I can equate this mv square over r, and just look at the magnitudes. I can equate this with evb. Since v and b are perpendicular to one another, sine theta is 1. So now what I could do, I could make this go into mv over r is eb. I can also find out the angular speed of this electron, the time it takes to complete one revolution, and that is going to be given by 2 pi over t. Now 2 pi over t is 2 pi over the distance that it covers, 2 pi r divided by the speed. So I have v over r. So I can replace this v over r with omega. So I'm left with omega equals eb over m. I can just put a small c, a subscript with this omega to denote this as the cyclotron frequency of the electron. So whenever I have an electron which is free to move, it's not bound to an atom, and it sees a magnetic field, it's going to go around in these circular loops. And it's going to do this with a certain time period, a certain frequency called the cyclotron frequency. And that is given by the strength of the magnetic field B. The higher the field, the faster will it go around and around and around in the loops. And we can also determine what the radius is going to look like. So R is given by mv over EB. And from this, I can determine what R looks like. So whatever the case is, we have the cyclotron motion of the electrons. Higher the magnetic field, smaller will be the loops. All right, so now what we would like to do is the following. Let's consider a solid. This is my x-axis. There's a y-axis, so I have x and y, and I have a z-axis. So this length, suppose, is Lx, This length is Ly. And this material, this piece of solid can have a certain thickness as well, which does not concern me for the time being, but it of course it has some thickness. And I apply a magnetic field that is perpendicular or transverse to the plane of this solid. This is my magnetic field. Now I would like to take a quantum mechanical approach to finding out what the energies of these electrons are going to be and how the energies are going to change, what is the dispersion relationship. So in today's lecture, I'm going to take an approach which is based on the first quantization, which means that I will write down the Schrodinger equation for this electron and solve this equation and find out what the energy eigenstates are going to be. In the latter part of the course, I'm going to solve the same problem with the tools of the second quantization. But that is left for the latter part of the course. That I will do when I talk about the integer quantum Hall effect. But today I'm going to stick to the first quantization. So now if I would like to solve the energy for the system or find out the energy eigenstates, I would need to write down the Hamiltonian. So we know that the Hamiltonian is given by, it has a kinetic energy term p square over 2m, where m is the mass of the electron, and some potential energy. We know that we can take the potential energy to be 0, which is our reference value. But on top of this, I also have a magnetic field. So somehow I have to incorporate the magnetic field. So the magnetic field occurs in two varieties. It seeps into this expression for the Hamiltonian in two particular ways. One is through a Zeeman term. So the second term that I've written here in the Hamiltonian is the Zeeman term. B is the magnetic field in a particular direction. S is the spin angular momentum. Mu B is the Bohr magneton. And G is the Landau G factor, which for an electron is almost equal to 2. And I think you've learned about this in your quantum mechanics 1 or your quantum mechanics 2 courses. So this is just the Zeeman effect. You have, and that's where this term comes from. This term is just an eigenvalue for this operator. If B equals S, B is pointing in the Z direction, then I would just need to take the Z component of the angular momentum operator. Okay, so G mu B over H bar. Now the Z component is H bar over 2 B sigma Z. So this G cancels out like this. So I have mu B B sigma Z. And the eigenvalues of sigma Z are plus minus 1. So the energies turn out to be plus minus mu B B. So that's where we get these energies from. The Zeeman effect has its origin in being able to write the energy in the form of this Hamiltonian. So this is a Zeeman term. It tells you what the spin splitting is. And we've already seen this when we were discussing the polyparamagnetism example. The first term also is modified. So in the presence of term here has to be replaced by the canonical momentum. And this canonical momentum is given by P plus Q A, where A is the vector potential. So P has to be replaced by P plus QA, which becomes P minus EA. Excuse me. All right. Now, have you seen this concept earlier in any course of physics? Have you looked at canonical momentums? I'm sure you've studied magnetic vector potentials in your electrodynamics course or your electricity and magnetism course.
इससे
So,
वेक्टर पोटेंशियल पढ़े हुए हैं प्लस कैनोनिकल फोर्सेस देखी हैं क्लासिकल मैकेनिक्स में, लेकिन कैनोनिकल वेक्टर कैनोनिकल मोमेंटम नहीं हुआ।
अच्छा, और ग्रेजुएट स्टूडेंट्स ने देखा, मास्टर स्टूडेंट्स ने?
सर अभी तक ना हमने इलेक्ट्रोडायनामिक्स का कोर्स नहीं लिया, वो हम नेक्स्ट जब ऑफर होगा तब लेंगे।
अच्छा, ठीक है। तो अभी तक तो हम ये फिर कहते हैं कि इन द प्रेजेंस ऑफ अ मैग्नेटिक फील्ड the P has to be replaced by the canonical momentum, which is given by this thing here. Now, why do we do that? Because it is only the canonical momentum which satisfies the Heisenberg's uncertainty relationship with the position operator. So if I were to take the commutator of the position operator with the mechanical momentum, the answer would not give me. So we know that x commutator with p x is going to be equal to iota h bar. However, in the presence of a magnetic field, this commutation relationship breaks down. However, if I were to replace this px with the canonical momentum, which is sometimes denoted by pi x, will this commutation relationship be preserved? So, and the canonical momentum is also gauge dependent, whereas the mechanical momentum is gauge independent. So for the time being, remaining within the scope of this course, let's take this as a matter of principle that whenever we have a magnetic field, we replace the momentum in the Hamiltonian P with P plus the charge times the magnetic vector potential. Okay, so now our Hamiltonian becomes P minus EA square over 2m plus minus G mu B over H bar S. I could put a Z here just because the B is pointing in the direction of the magnetic field. Now this is my Hamiltonian. And if I were to solve the energies or find out the energies, I would just need to solve the time independent Schrodinger equation, where this psi is now a function of x, y, and z. And let's see how we go about solving this problem. Okay. Now, first of all, we do know certain facts. This P, let's look at this vector potential first. Now, the vector potential is defined such that if I take the curl of this vector potential, I would get the magnetic field. All right.
All right.
But yes. Any question? So this is a Maxwell's equation.
This is a Maxwell's equation.
Sorry. Can you just mute your microphone, please? Okay, let me do that. Okay, so this is a definition of this is a definition of the vector potential. Now, the point with this vector potential is that I can replace this vector potential with something of this kind. I can add the derivative or the gradient of some other scalar potential, and still if I were to take the curl of this new A prime, I would still get the same value of B. So there is some choice that we can make in choosing our A. We can add the gradient of any scalar field to A and still get the same magnetic field. So this choice that we can make is called the choice of the gauge. Whatever gauge we choose, the energies that come out as a result, they are going to be gauge independent. They are not going to depend upon our choice of the gauge. So we can make our calculation simpler by choosing certain gauges. So if I were to choose what is called the Landau gauge, I can choose a particular, I can choose Landau gauge which looks like this. So my vector A, which is a vector potential, can be written down as minus by 0, 0. So this is minus by pointing along the I direction. Now y is the variable y, plus 0 along the j, plus 0 along the k direction. So let's choose this gauge for A. First of all, we would like to find out whether if I were to take the curl of this vector potential, do I get P? So if I take the curl of this A, now how do I define my curl? I just need to find this determinant. So curl is this thing minus by 0, 0. So you will notice that if I were to take, so this gives me 0 I minus 0 j plus bk, and this indeed is my magnetic field, right? So a magnetic field B pointing along the k direction, that is indeed my magnetic field. Remember that here k is the unit vector along the z direction. So if I were to choose this A, this vector potential in this form, it will indeed recover the correct B. Now B is something physical, B is something measurable. So this choice of gauge works. So let's proceed with this choice of gauge. We can choose other gauges, by the way, as well. For example, we can have 0I plus bxj plus 0k. We can also have symmetric gauges, which are called Coulomb gauges. But let's stick with this choice of gauge and proceed. Okay. So this choice of gauge works because if I were to take the curl of this vector potential, I will get the correct magnetic field. Now what I need to do is my A just has an x component. And this is a vector here. And I'm taking the modulus square of this vector. And P has components. So the mechanical momentum P has components Px, Py, and Pz. So let me write down the Hamiltonian again. P minus Ea squared over 2m minus G mu B Sz over h bar B. Okay. So I can write this as P x minus EBY. So this is the x component of the canonical momentum 2 pi 2m plus Py square over 2m plus Pz square over 2m minus G mu B Sz over h bar B. So this is my Hamiltonian. I've just expanded this canonical momentum into its three components along x, y, and z. This is the x component here, this is the y component here, and this is the z component here. Because P after all is a vector. Any questions? So now let's look at this Hamiltonian. My trial solution will be a function of x, y, and z. Now what you will observe here is that I could write down my solution, my trial solution or my ansatz in the following fashion. This there's a px here, and there is a py here, and there's a pz, but there is also a y term here. So what I could do is I could write my trial solution as, and I can break it up into the x part, the y part, and the z part. This is what you generally do when you would like to do a solution by separation of variables. So this pz square here would want me to write the z part of the solution as a plane wave, i kz z, and this px would want me to write down the x part as a plane wave along the x-axis. But this y here is slightly confounding, it's slightly confusing. So I would keep this totally arbitrary. I would put this as phi as some function of y. So I have a plane wave along the z direction and I have a plane wave along the x direction. And I factorize out my solution into three parts: an x part, which is plane wave, a z part, which is a plane wave, and some arbitrary function of y, which I denote as phi. Now what I need to do, I need to take the Hamiltonian that I have over here and act it upon the wave function and find out what the energies are going to be. Now this term here, so this is my, let's call this the third term, let's call this the fourth term. So if I look at the third term, pz square over 2m, and I just look at this trial solution here, eikzz eikxx phi y. So I know that my pz is minus iota h bar partial z squared over 2m. And all of this acts on eikzz eikxx phi y. Okay. So minus iota square is going to give me iota square, which is minus h bar square over 2m. And this acting upon this gives me ikz twice. And I'm left with the original. So ikz square gives me h bar square kz square over 2m. So this term gives rise to a contribution in the energy equal to h bar square kz over 2m, which is very simple. This is just like a free particle in the z direction. So if I have a free particle that is bound to move in the z direction, it's one-dimensional particle, this z part of this equation is going to give me a free particle solution. Free particle wave, a traveling wave, eikzz, with energy h bar square kz square over 2m. We've already seen what the fourth term gives. The fourth term gives us an energy plus minus mu bb. This is the fourth term. And the fourth term, of course, is is uh, a spin part. Okay. And the spin part has nothing to do with momentum operators. Okay. The spin part is totally separate. So it's a spin degree of freedom, but it still contributes to the energy. Whatever energies we get from the orbital parts, the spin parts add to those energies. So the fourth term in the energy is plus mu vb. The third term in the energy is h bar square kz square over 2m. Any questions? Were there any questions, my friends? Yes, Mariam.
Sir, how have we made this choice of wave function?
So first of all, it's an ansatz. It's a trial. It's a trial. So this is conventional practice that in whenever you want to solve the Schrodinger equation, the time independent form, we take a trial solution. That's what we did in a particle in a well. That's what we do for tunneling experiments. But looking at the Hamiltonian also gives us a clue. So this third term is the only pz term. So if I just have a free particle, we know that for a free particle, the Schrodinger equation yields a traveling wave, a freely propagating wave along that particular direction. Okay, so that's why our Z component of the trial solution has a waveform, has a traveling wave structure, which is EIKZ. Similarly, if you look at this term here, Py, if you look at this term here, there's a P, if you open up this bracket, this is going to give us a Px squared term. And the Px squared term also has a trial solution. It admits a wave function of the form EIKXX. But we are unsure about the y part because we have this y term here. So we just put all the y dependence of the solution into an arbitrary function, which we label as phi. Okay, so this becomes a trial solution, and then we see whether it works or not. So we see that it works for the third term. We see that it works for the fourth term. Now we would like to see whether it works for the first and the second terms. Okay, so did I answer your question?
Yes, sir. Thank you.
All right, so now our intention is to look at these terms here. Okay, so these are the first and the second terms. So let's focus our attention on these terms. So this is the third term, the first and the second terms. So the first and the second terms have this form Px minus Eby. This is also an operator, square over 2m plus Py square over 2m. Let me call this H1 just for simplicity. Now, if we just try to change the factors a little bit, we get EB square y minus E over EB square plus Py square over 2m. All right. Now we've seen that omega c, our cyclotron frequency, is given by EB over m. Omega square c is EB square over m square, which is EB square over m square. All right. Okay. Sorry. That's it. So this term here, this prefactor, can also now be written as m half m omega c square. Okay, so this makes the first and the second term in the Hamiltonian comes out as half m omega c square y minus, now let's call this thing y dot, y dot or y naught or y zero plus py square over 2m. All right, so far so good. Now this term, this Hamiltonian here, so where we have defined y naught to be px over 2m, px over eb, sorry. Now does this form of a Hamiltonian ring a bell? Does this look familiar?
Harmonic oscillators.
Exactly, clapping. Yeah, shabash. This is really a harmonic oscillator. In 2 dimensions, which are the x and y dimensions, because this has an px factor. So anyway, this is a harmonic oscillator. This is a kinetic energy term, and this term here is simply a potential energy term. If I ignore this thing for a time being, just ignore this y naught, then everything would have been really clear. This potential energy term would simply be equal to like half ky term, ky squared term, which is just the potential energy of a harmonic oscillator that moves along the y-axis. If I subtract y naught from it, it really means that this harmonic oscillator is translated along the y direction by y naught units. And finding the energy of this system. Now, this is a quantized harmonic oscillator. Any harmonic oscillator, as you know, we can find out the energies of that system. So if I have a quantized harmonic oscillator, I already know that its energy levels are quantized. A harmonic oscillator which has a Hamiltonian of this form, half m omega squared, some frequency squared, could be the cyclotron frequency, could be anything, y squared plus py squared over 2m. If I were to solve the energy structure of this Hamiltonian, what would I get? What are the solutions for this one-dimensional harmonic oscillator? What would the energies look like? So this black curve is a graph of, so you could say, is a graph of the potential energy versus y. Vy is half, m omega square is nothing but k y square. So if I were to solve this Schrodinger equation, have you solved the harmonic oscillator in your quantum mechanics class?
Yes, sir.
जी कौन बोला है?
Sir, both.
बाकिर?
जी.
अच्छा, तो कौन सी क्वांटम मैकेनिक्स 1 में कि 2 में?
Sir, 2 में.
ठीक है. So energy structure कैसा लगेगा इसका?
Sir, for the nth energy level, I guess n plus half times h bar omega.
Exactly. So the energy levels are quantized. The harmonic oscillator cannot pick up any energy whatsoever. The energy levels are rather quantized. And those energy levels are quantized by some quantum number, let's call it L plus half h bar omega. And in our case, this becomes omega c. And what this term does simply is that it changes the minimum of the energy of the energy potential. So the entire curve, in a sense, is shifted to the left or to the right by naught units. Okay. So now we can combine the first, second, third, and the fourth terms together, and we can find out the energy for these free electrons when they are exposed to a magnetic field. And those energies are now quantized by this quantum number L. Okay, and the energies are going to look like L plus half h bar omega c plus h bar square kz square over m plus minus mu bb. All right, so this is the energy of an electron, free electron, independent, non-interacting electron, when placed inside a magnetic field, when its orbital motion or its spatial motion is also taken into account. The electron in the classical sense is making these cyclotron orbits, but the energies of these electrons, the sea of electrons, becomes quantized. Now let's look at the structure of this equation. Now, if you look carefully, this energy only depends upon kz. So it acts like a free particle along the z direction. and the wave function is a plane wave along the z direction. And in the xy plane, in the transverse plane, the plane in which this plate exists, the energies are quantized. So if I were to make a plot, so let's ignore this for the time being, because this term, unless b is really, really large, this term is much, much smaller as compared to the quantization terms h bar omega c. So if I were to plot uh, with this, so if I make the k here, if I on this axis, if I were to plot kz, and I were to now plot the energies are going to depend upon L. So I will get a curve for the energy for L equals 0. So this is my L equals 0 curve. And this is above the 0 level by h bar omega c over 2. So the lowest energy of an electron in the presence of a magnetic field is given by h bar omega c over 2 plus h bar square kz square over 2m. Now kz can take up all of these values. It looks continuous, even though if we were to take the finite extents of the sample in the z-axis, we already know that we will have discrete points along the z-axis as well, along the kz. So not all values of kz are allowed. But if you look at the macroscopic scale, these kz points are placed so finely together that we generally draw this continuous curve. Now, if this is the ground state of the electrons in the presence of a magnetic field, I could also draw the L equals 1 level, which is another parabola. But now this parabola is shifted upwards from the previous parabola by units of h bar omega c. This is L equals 1. Likewise, I will have L equals 2. I will have L equals 3. I will have L equals 4. So this process in which the energy of the electron becomes quantized is called Landau quantization, and these levels are called Landau levels. Any questions? Now if you, okay, so now what I would like to do now is the following. I would like to look at the structure of the K space in the presence of a magnetic field, in the presence of Landau quantization. ये समझ आ रहा है या थोड़ा सा मुश्किल हो गया? बिलाल,
थोड़ा मुश्किल है लेकिन समझ आ भी रहा है.
आ भी रहा है. So Bilal, can
100%
you
कह रहा है,
just
it's
summarize?
something like
हाँ,
80
बोले?
85%. जी.
देखो, what we've done, let me summarize in simple English. We have an ensemble of free electrons. We expose it to a magnetic field. Then what's going to happen is that the energy is going to get quantized. The electron will be at the freedom to choose so if the magnetic field is along the z direction, its motion along the z direction is not going to be affected, correct? So when you
Yes,
have
sir.
a solid, when we looked at the quantization of the electron gas, we proposed a wave in the x direction, a wave in the y direction, and a wave in the z direction. So if a magnetic field is along the z direction, nothing happens along the z direction. There is no cyclotron motion along the z direction. Everything happens in the xy plane, because the force, the Lorentz force q v cross b, is a vector product of v and b. So nothing happens parallel to b. So along the z direction, the wave remains a plane wave, and the energy is still given by h bar square kz square over 2m, like any other free electron gas. So this electron gas remains unperturbed in the z direction or parallel to the magnetic field, nothing happens. However, in the transverse plane, which is perpendicular to the magnetic field, things change. The Hamiltonian takes the form of a harmonic oscillator, which is displaced with respect to y equals 0. It goes to y naught, and y naught we defined as px over eb. So it will have certain wave functions, which I'm going to come to in a minute. But nevertheless, if you solve the quantized harmonic oscillator using the rules of quantum mechanics, ladder operators, second quantization, etc., we'll obtain quantized energy levels. Now, if we didn't have any kz term, these quantized energy levels would just be equally spaced like any other harmonic oscillator. But now, since we have to add the half kz squared terms to them, these levels get curved like a parabola. Now, this is the L equals 0 quantized Landau level, L equals 1, L equals 2, L equals 3. Okay, so now we have a sequence of parabolas when plotted along. So this is E versus Kz. Whenever we make a diagram of this kind, E versus Kz, or frequency versus Kz, such a diagram is called a dispersion relationship. So the dispersion relationship is now turning out into a sequence of parabolas. Nothing exists between the parabolas. All Kz's are possible, taking into account, of course, the fine-grained structure of Kz because of the finite size of the object in the z-axis. When we apply the boundary conditions, Kz becomes quantized, we know that. So taking into account that quantization of Kz, Kz takes a continuous range of values, but the energy becomes quantized overall. So this is Landau quantization. Now what I'm trying to do is I'm going to look at how the K space changes in the absence of a magnetic field. If I were to plot the K space for this free electron, I'm going to get these points like a three-dimensional grid. And if I were to, for visual clarity, draw these as a skeleton, you can draw another net above it. So I will get this mesh of three-dimensional points along kx, ky, and kz, and kx I know is nx 2 pi over L, x, ky is ny 2 pi over Ly, kz is nz over 2 pi over Lz, and I would also know that I will have a Fermi sphere. All the k points within that Fermi sphere, they are going to be occupied. And the Fermi sphere represents the boundary between the occupied and the unoccupied levels. Okay. Now, how does this K structure change? This new energy structure gives rise to a new K structure. And what is that? Now, if I were to plot, now this is, I need to draw a really nice diagram to show this, how the K structure changes. This energy here has a kz squared term. It does not have a ky squared term. It does not have a kx squared term. So what's going to happen is the following. First of all, if I were to look at this term here, I see that my harmonic oscillator potential is displaced along the y-axis, right, by this much, y naught. And this y naught, let me redraw this diagram. So this is my potential, effective potential. This is my y, and here I'm plotting Vy, which is half k y minus k square, or excuse me, I forgot I could erase my wrongdoings here. Half m omega square y minus pi naught whole square. Now this of course is this variable here. Y naught is px over eb. So this point here is y naught. So px, we all know that if we were to find the eigen energies of px, you'll get h bar kx eb. So this y naught is really h bar kx over eb. So the x component of the k vector determines the center point or the pivotal point of the wave functions. So if we were to solve the Schrodinger equation with this displaced potential, then the wave functions, we all know that the solutions of the one-dimensional harmonic oscillator, they are Hermite polynomials. So the zeroth order wave function is going to look like this. First order wave function is going to look like this. Second order wave function is going to look like this. So these Hermite polynomials have as their center, they're shifted with respect to 0. And the amount of shift is given by h bar kx over eb. Now we also know that if the wave function really exists inside the solid, this y naught has to be within the length of the solid. So this y naught, so the length of the solid is Ly. So let's take this to be the y-axis. So the length of the solid is Ly. We can call this to be Ly over 2. We can say that this end is minus Ly over 2. So the y naught has to be between minus Ly over 2 and Ly over 2. So this means that my h bar kx over eb has to remain within these limits. Just by logical arguments, the wave function must have its center inside the solid. Otherwise, the wave function, there's no point in having the wave function go out of the solid. So there's a constraint on the value of y naught. Now, what we could do is the following. My kx has to be between minus eb ly over 2h bar, eb ly over 2h bar. Okay, so now if I were to draw the kx axis, my values of kx are confined between eb ly over 2h bar and minus eb ly over 2h bar. But I know that the spacing between any 2 points along the kx axis, that has to be equal to 2 pi over lx. So the number of points I have in this range is going to be equal to this entire span, which is this quantity subtracting, which subtracts this quantity, and that is going to be eb ly over 2, and I divided by the spacing between the 2 points, which is 2 pi lx. So I'm left with eb over 4 pi lx ly. There has to be a eb 2h bar bhi hai, eb ly to h bar. All right. So this is the total number of points in the K space that I have corresponding to one Landau level. Now, why one Landau level? Because we're talking about a single wave function here. For the next wave function, we'll have a higher value of L. So we just focus our attention on a fixed value of L at a fixed magnetic field. So let's focus our attention on this L equals 0 level. Its Y naught has to be within the size of the sample. This puts constraints on the range of kx that are allowed. Now, all of these kx's belong to a single L. So all of them belong to a single L. For the next L, we'll have a similar expanse of kx's. Okay. So at a fixed magnetic field, at a fixed value of L, this is the range of kx's that are allowed. Now, when I have the range of the kx's that are allowed, I can look at this number line of kx's, and I know the separation between two kx points is going to be 2 pi over Lx. I can count the number of kx points that belong to one value of L. So this is the total number of allowed kx values that belong to a single value of L. And if I were to take into account the spin degeneracy, which is the fourth term of plus minus mu b, each point can harbor 2 electrons with opposite spins. So the total number of states that belong to an L value is along the ky plane is going to be twice of this, which is EB 2 pi h bar Lx Ly. And this h bar is the reduced Planck constant. I can make this EBH Lx Ly. Now, what this means is something really nice is showing up. This Lx Ly is the total area of the solid. This is B. This is E. Excuse me. Right, so just a minute. I think my cells need a bit of a makeover. So any questions in the meantime while I change my batteries? I need to change my own batteries too. So any questions?
सर यहाँ पे जो हम B यूज कर रहे हैं तो it's just the magnitude of our field, right?
Yeah, just the strength of the magnetic field.
ठीक.
Sir, जो B है, is it along the z-axis?
What? What
The
is along?
B.
The B is along the z-axis, yes.
Always here?
Yeah, in this example, yes. So the cyclotron orbits are formed perpendicular to the applied field.
Okay.
Because of the Lorentz force, because there's a vector product there in the Lorentz force. So I think I need to restart my thing. Can I make someone the host, or let me see if I can make someone the host. Excuse me. So I'm making Bakir the co-host. I'm going to pause the recording for a minute. Resume the recording. Let me share my screen again. All right, so so my h bar kx is this thing. My separation is EBLY over, so this factor of 2 is extra here, sorry. So the number of points I have is given by this point minus this point, which is EBLY over h bar, this thing here, and I divide this by the separation between two consecutive kx points, which is going to give me 2 pi over lx. And when I did this, just h bar EBLXLY, this is a 2 here, 2 here, 2 here, sorry, 2 here, and and the number of states I take into account the degeneracy factor. I multiply all of this with 2, this 2 goes away, and I'm left with a 2 here, 2. So h bar, this becomes h, and the 2 here. So now this is Lx over Ly is the area. I multiply this with B, and I have 2 times E over H. So this is the total number of states belonging to a single value of small l. The total number of states in the kx, ky plane. And if you look at this expression here, a really important expression, B times area is nothing. What is B times area? Is the flux that passes through this area. Okay. And this factor H over E also has units of flux. It has dimensions of flux. So let's call this phi naught. So this phi naught is the elementary quantum of flux. Just like small e is the elementary quantum of charge, phi naught H bar over E is the elementary quantum of flux. It's really important. It's a really important concept. So what we observe here is that even though all values of Kz are allowed, which are within the constraints of quantization of Kz, the Kx and the Ky points, they are all now belonging to the same value of L, and the distinction between those Kx and Ky points has gone berserk. There's no distinction between the Kx and the Ky points. All of those Kx and Ky points belonging to a single value of L, they are now appearing together. Now, if I were to draw this on the on the K Cartesian Kx, Ky, Kz plane, this is the picture that emerges. Yes, Mariam.
Sir, जो ये elementary quantum of flux है, is this a vector quantity?
No, it's a scalar. H over E. It's a scalar. Flux is a scalar.
Okay. But sir, B हमारा K direction में था तो उस वजह
तो
से
अगर ये देखो ना, ये B है ना, this is B is a vector. The area is also a vector. So the area, if I draw the area vector, which is perpendicular to the surface, I can find the dot product of B with dA.
Okay, ठीक है sir, सही
I
है.
can integrate over the area. This gives me flux.
Alright.
Okay. So now what we're trying to do, I'm trying to make what the picture looks like in the K space. So all values of Z are allowed. So let me first draw the let me try drawing this. Let me draw the Fermi sphere. Okay, not a nice drawing, but nevertheless. So let me try doing this in a better fashion. So this is my Fermi sphere. Inside this Fermi sphere, I have k points, which are all quantized. They are on a regular grid. This is the reciprocal space. Now, what's happening is that I can, let me first draw. Let me first draw the diagram and then I'll explain it. So this is my kx. Kz. Change the color a little bit. All right. All values of kz are allowed. For a particular value of L, kz can go up to minus infinity to infinity. Of course, you have to remain within the Fermi sphere because the number of electrons that are available to fill up those points, they are finite because the solid has a finite size. So the number of electrons does not change overall. That constrains the up to where you could go, and that is the Fermi sphere. But for a given value of small l, all values of kz are allowed, and the kx and the ky points, they are all the number of those points is given by this expression here. And the distinction, the energy does not have any dependence upon kx and ky. It only depends upon kz squared. And it depends upon kz squared. And the other thing is that the number of points belonging to each value of L is now determined by this factor. 2 times phi over phi naught. Okay. Now all of those kx and the ky points, they coalesce onto this tube. So if I make a longitudinal section of this diagram, this is a tube in the middle of the Fermi sphere, and it's a vertically pointing tube. All of the kx and the ky points whose number is given by this, and this is called nothing but the degeneracy of a Landau level. All of these states coalesce onto the Landau tube. This is called a Landau tube. I think this object has given up now because I think it's become a very heavy file. So the inner tube is now a cylinder or a Landau tube, and it corresponds to the L equals 0 tube. All of the kx and the ky points whose number is given by 2 phi over phi naught, they now lie on this tube. Likewise, we can draw another tube, a bigger tube, which is the L equals 1 tube, which is coaxial with the L equals 0 tube, but it's outside it. And the same number of points now coalesce on the L equals 1 tube. All the kx, so just imagine that you have a file of soldiers. The soldiers are standing around in different directions, and they're randomly distributed. A magnetic field is applied, and all of those soldiers gather together in concentric circles. and there's nothing in between those concentric circles. This is what is happening in Landau quantization. Sorry, I just my if I only wish my stylus didn't stop working here. But now I have these concentric Landau tubes, one after the other, one after the other. The structure of K space becomes totally variegated. It becomes totally punctured in a sense that not all kx and ky values are allowed. The structure breaks down into these concentric tubes, and as it breaks down into these concentric tubes, certain gaps appear between the tubes. No k points are allowed between the tubes, and a number of points, which is given by the degeneracy, all of those points coalesce onto a particular Landau tube. So the structure of the K space becomes totally different from what it was in the absence of a magnetic field. So this is what I just wanted to describe about Landau quantization, and this results in extremely interesting phenomena. Now we see that the Fermi sphere that intersects this Landau structure, these energy level structures, it does not intersect the Landau structure in a uniform manner. If all the k points were equally populated and they were equally spaced, they're still equally spaced. The spacing between these Landau tubes is fixed. It's determined by h bar omega c in a sense, but now the interaction of the occupied energy levels with the Fermi sphere, where the action takes place, where the conductivity takes place, is becoming corrugated, and the density of states is no longer a fine square root relationship. Rather, it's one dimensional along the z-axis, and it becomes slightly more complicated, and it's beyond the scope of this lecture. But I've derived this in another series of lectures that I gave on solid state magnetism, which can also be seen online. So the density of states can be derived, and I've derived the density of states in that particular series. But any questions about Landau quantization, I would like to stop here. Homework number 5 has been uploaded. It's a shorter homework, but it's due next month, next Friday, next Sunday, sorry, Sunday night, so that we have ample time on Monday to look at the solutions, so that you can prepare for the midterm on Tuesday. So any questions about Landau quantization? And this is a really important concept. Most of modern condensed matter physics, especially when we are dealing with low dimensional systems, two-dimensional electron gases, starts with the discussion of Landau quantization. The integer quantum Hall effect, which won the Nobel Prize in the 1980s, starts with Landau quantization. The fractional quantum Hall effect, the spin quantum Hall effect, the idea of topological insulators, quantum spin Hall insulators, Chern insulators, all start with the discussion of Hall effect. And Hall effect was discovered back in the early 1800s by Edwin Hall. Who knew that after 200 years of the discovery of the Hall effect, this uh, this field would take a resurgence, and it would take a U-turn in the positive direction. So this is a really important concept, by the way. It's the linchpin of modern condensed matter physics. So any questions before we call it a day? Yes, Bilal.
सर आई हैव अ क्वेश्चन रिगार्डिंग द फर्मी स्फीयर। तो सर जो हमारा फर्मी स्फीयर जो आपने भी ड्रॉ किया हुआ है फॉर लैंडौ क्वांटाइज्ड लेवल्स, तो इसका जो सेंटर है ये हमारे ओरिजिन पे है, हमारे एक्सिस
जी
के जी के
जी
वाई।
जी जी।
और जो हमने पहले ड्रॉ किया था फॉर द स्क्वायर वाला जिसमें रिलेशन था, उसमें भी हमने सेम सेंटर में ही रखा हुआ था उसको।
वो तो देखो ना, वो तो डेंसिटी ऑफ स्टेट्स थी।
हम्म
ये डेंसिटी ऑफ स्टेट्स नहीं है, ये तो के स्पेस का स्ट्रक्चर है। स्क्वायर रूट ई रेज पर हाफ या ई रेज पर माइनस वन हाफ, वो तो डेंसिटी ऑफ स्टेट्स है। The density
हम्म
of states in this particular case, if my stylus were working, I would have show that it's probably I'll do this at the beginning of the next lecture. It's very interesting.
ओके
It's a
क्योंकि सर
it's one
मुझे याद
dimensional,
था।
so it's one dimensional convolved with a two-dimensional density of states. Very interesting.
ऑलराइट, क्योंकि सर मुझे याद था स्टैटिस्टिकल मैकेनिक्स के कोर्स में कि व्हेन वी यूज्ड टू फिल अप द फर्मी लेवल्स, तो हम जो अपना स्फीयर था उसका 1/8 बस फिल करते थे फॉर द लेवल्स, और जो उसका सबसे ऊपर वाला लेवल होता था डिफाइंड द फर्मी एनर्जी और केमिकल पोटेंशियल। सर इस सिचुएशन में जो है हम उसको 1/8 फिल कर रहे हैं या फिर इज इट फिल थ्रू आउट?
It's
आई
filled
कैन
throughout
गेट।
because kx, ky, kz can take positive values, and they can also take negative values as well.
So these are circles अगर इसको हम ऊपर से x z axis से देखें.
Yes, so these are circles, one after the other. These are rings. So unfortunately, my stylus is not working. I intended to show that these are rings, concentric rings, when viewed from the top.
All right, sir. ठीक है. Thank you.
And they are so positive and negative values of kx, ky, and kz are allowed. Okay. Now, when you draw in the n space, so you remember that kx equals nx 2 pi over l, and nx, ny, and nz, which are the quantum numbers, they can take a positive value. So if you draw not the k space, but the occupation number representation space, which is the n space, only then you need to take the octant, one octant. That's when nx, ny, and nz cannot take up negative values. They start from 0 and go up to infinity. Okay, so that's when you take the octant. But here we're talking about k space values, so they can be positive and negative. And when we take the energy, we take the square of these k values. So the negative k's also contribute to the energy, as do the positive ones.
Okay, sir. Understood.
ठीक है, वो n था जब आप मेरे ख्याल में ऑक्टेंट्स की बात करें ना, वो सिर्फ n ऑक्यूपेशन नंबर रिप्रेजेंटेशन थी.
Yes, उसमें n करते थे हम.
इसमें भी कर सकते हैं, फिर आप ऑक्टेंट ड्रॉ करेंगे.
हाँ, उस तरह भी हो जाएगा. ठीक.
चलें जी, थैंक यू वेरी मच, बहुत शुक्रिया. होमवर्क नंबर 5 ज़रूर करें, बड़ा इंटरेस्टिंग है, छोटा सा है और कैलकुलेशनल है. तो सी यू ऑन थर्सडे. वी गोइंग टू स्टार्ट अ डिस्कशन ऑन द बैंड स्ट्रक्चर. अच्छा जी, खुदा हाफिज.
अल्लाह हाफिज़ सर.
सर इसके लिए ना कोई फर्दर रीडिंग मटेरियल बता दें.
ये जो
आज का लेक्चर है.
आज का लेक्चर है, ठीक है, मैं देख के बताता हूँ आपको. ये मैग्नेटिज्म की किसी बुक से मैं आपको देख के बताऊंगा.
चलें ठीक है. थैंक यू.
So you wanted to discuss, let's end the recording, just a minute please.